Wonderful. Thanks so much for having me there. I first want to mention that it's highly topical because a Nobel Prize just went to Imbens and Angrist, two people that had very strong influence on the way I think about causality. And I want to thank all of you for being there. And I also want to apologize for not being there. The reason why I'm not there is because I became an American citizen today. And if I had left the country, I would have had serious trouble with my work permit and I wouldn't have managed to come back. In any case, let's dive right in. What's the definition of causality? Let A and B be events. Causation exists as if we had changed A to A star, the probability of B would have been different. And that's arguably causality defined as such. That's the counterfactual definition of causality, plays into just about anything we do and I think how we think, which is where is it important? No, it's important if we want to predict randomized perturbations. It's important if we really want to understand a causal chain, because if we say something like a neuron makes another neuron fire, it's always a causal commitment. And then arguably, if we want to really understand mechanism, we want to get a step further, not just say here's a causal chain from A to B, but also what are the mechanistic elements that get us from A to B. And arguably, causality is the central question in machine learning and life. No, in our life, as well as in machine learning, there's always a purpose, which is we kind of want to make the world better for us or for the way how we conceptualize the world outside. For example, if we do classification machine learning, we only do it because we want to act on the results of classification. And ultimately in our lives, the central question is a causal question, which is, if I choose A over B, would the world be better in however I define better? So it's arguably important. So what do we do as neuroscience when we do that? And there's many very different approaches that people take for that. For example, you can have perturbations, no? Like you can have optogenetics, you can have TMS producing perturbations in the brain, and then sometimes people get metal rods right through their brain. But this approach very cleanly establishes causality. No? Like at least the causality from light goes in and behavior happens in the case of optogenetics. A big problem is the perturbations that we can always do are always low-dimensional perturbations. It's usually expensive or rare. It can be unethical or dangerous. So while perturbations are the gold standard for establishing causal relations, the problem is that often we can't do them. What else do we do? We sometimes do model comparison, where we can say we have two models with distinct internal causality. We choose the model, the one that's better, hopefully at p smaller than 0.05, and we can, for example, use things like archaic information criterion. The problem is that that doesn't need to describe causality, in particular if the ground truth model isn't part of the models that we compare. Now, so with that, we can say which models are better, but it's not clear if going down the gradient of models in a way would ultimately get us towards veridical models. We can also use saturated structure equations, as the economists would call it, and relating to directed acyclical graphs. And the important thing is that to be aware of the assumptions, causal sufficiency or unconfoundedness. We basically need to have the variables that matter in our set, and we need to make sure that we don't correct for variables that could be colliders. And we need to also know the correct functional form. There's a beautiful paper by Lafayette there. But I first want to give you a little bit of an intuition on causality. So I think in our heads, we always have this notion that correlation and causation are very similar. And I want to give you, I think, the reason why that is the case. So let's say we set up a very simple system. Xt plus 1 is sigma, which is some kind of a nonlinearity, times axt plus epsilon t. Okay, so we have a system, we have Gaussian noise on the inputs. The scaling doesn't really matter here. In fact, the results that I will show you, the sigma basically doesn't matter unless you really overdo things here. You can say A is now the ground truth causal connectivity matrix. Like A is in the system that I'm talking about, the actual set of causal influences. And then we'll initialize it to x0, and then we make sure that the A doesn't lead to instabilities. So we make sure we set it at the largest singular value. So in fact, we'll be switching to the linear case here. We make it that the largest singular value is 0.99, because if it's larger than 1, of course, things will diverge. So, and then what we can do is we can say, now in such a system, we expect that the correlation between one time step of one simulated component, which we could think of as a neuron, and I will call it a neuron, on another that relates to the time delay one correlation of the neuron with another neuron. Now, how close are those two? Now I can compare now A with the correlation matrix of xt with xt plus 1. And indeed, they're super similar. Now what we have here is we have a simple simulated system, 6 neurons, and I should mention here, this is part of the Neuromatch Academy materials. If anyone is interested in more details, the full code and videos describing it and so forth are there. And now you can say on the top, we have the true connectivity matrix. I should have said we also choose it according to some from a sparse set of matrices. And then what we see below is the time delay one correlation matrix. And look, those two are like so similar. So in this small system, correlation and causation are just very similar. In this case, they're like really like 0.95 or something correlated. Now this is in a small system. So let's say we take the same intuitive, simple system and we make it bigger. This is what we have here. We have the true connectivity matrix left. Now we have the estimated connectivity matrix, which again is just the time delay one correlation matrix. And now they're entirely different. So in these small systems, the kind of systems that we can simulate in our heads, correlation and causation are very similar. But if we go into systems that we can't simulate in our head because they're bigger, say 100, then correlation and causation start being very different from one another. And so this is what we have here with the analysis for that same dynamical system I told you about as a function of the number of neurons. What's the correlation of the flattened matrices, A, the causal matrix, and R, the delay one correlation matrix. So what we have is outside of that range where we can meaningfully simulate them in our head, correlation and causation become arbitrarily different. Now, you can say, in this case, if I would record from all neurons, now like this is a pairwise analysis. I just take a neuron and a downstream neuron. What if we had lots of variables, and like if I don't look just as pairwise correlations, but I looked at maybe a lot of neurons and I would be doing some correlation, some corrections. In this case, we might still expect that there's some variables that we record from and some variables that we don't record from. Not like the world record, it keeps getting better at how many neurons we can record from. But I believe no one has ever recorded from more than 2 million neurons, and at high resolution, those numbers are, of course, much lower. So let's look at the so-called omitted variable bias equation. It's an equation that is very popular in econometrics. In fact, very popular in the domains of econometrics that the Nobel Prize was given about. The idea is the following: I have a couple of variables that have dynamics between them. Everything is linear here. Now what we have is we have some outcome yi, and that yi is linearly related to the variables that I observe, the xi, with beta, which is what I want to estimate, arguably. But then there exist other variables that I don't measure, which are the zi's, that also have an influence on delta, but I don't observe them, plus noise, which in this case they call ui. Now you can say, well, how is that going to affect our estimates? Well, it means that the estimate that we're going to get, beta hat, is going to, just like in regular regression, there's going to be a term, which is the inverse of the covariance matrix, x prime x to the -1 times x prime. And then what we have is we have this new term that we just put in here, x beta plus z delta plus u. And then we can say, what is the expected value that we will get for our estimate beta? Now, basically, what we're trying to get at is how will we be wrong if we ignore the variables that we don't record right now? And what we have here is that the expected value is beta, which is good. That's what we want to estimate. And then we have this extra term, which is the x prime x to the minus 1 times the expected value of x prime z given x times delta. Now, keep in mind that in neuroscience, in lots of situations, we might record from hundreds, thousands, or even maybe 1 million variables. But there's still many, many orders more of variables that we don't record from. And keep in mind that this term that we have here for the omitted variable bias takes on the exact same form as the one that we have for the beta. So therefore, if we have far more dimensions that we don't observe than dimensions that we observe, we expect that this is going to be very large. In particular, given that this delta that we have, which are the correlations with other, that the x prime z, which is the correlations with other unobserved variables, generally are of order of 1, like there might be 0.1, 0.2, 0.3 or something. So what the effect is that the bias will be very large. Now, a lot of people, when I tell them that I'm worried about biases from variables that they don't record, tell me, well, look, how many more subjects do we need to recruit? It turns out that this is what it will converge to in the limit of an infinite amount of data. This bias doesn't go away. No amount of having more data makes that bias go away. And therefore, if we're in this domain where we record only from some dimensions in a very big system, we should expect our biases to be arbitrarily large. Now, let's now what I had so far is about causal validity. Now, like it's basically the biases that we should observe from not having all variables. Now, I recently started thinking about a little. Well, what if these guys push it so that we can record from all the neurons? Could we, in that case, identify the weights of all the neurons? And even that might be difficult. Because we can calculate what's the variance of the estimator. So what we have here is we have the variance of the linear estimator of calculating the difference between the estimated values and the real values. In this case, with fully observed signals. And now this has two terms. It has the sigma p term, and it has the square root p over n. So what we see here is the amount of data that we need grows linearly with the number of dimensions that we have. Let's say we have a typical neuron, has 7,000 inputs in this case, and let's say we need 100 seconds, or we need a certain amount for each of them, then we have to choose what's the signal to noise that we want, and we can say typical neurons spike once per second, and we can also say that typical neurons might be Poisson spikers. And of course, we can get much more information if they're not. And then you can say, in this case, if the inputs were white, if they were all uncorrelated, how long would it take? Well, it would take 100 seconds, which is 100 spikes to get 10% noise to signal. In this case, we need 6 days. But things, of course, get much worse because we can look at here at the Stringer data, where we can say, in reality, we have some large singular values and we have some small singular values. If we want to get the small ones to be right and not just the big ones, then we effectively need extra data that is proportional to the relevant condition number, which might be here in the order of close to 1,000, even if we just look at a data set of the size that we have. Now, of course, we don't know all the data. It could be that the neurons that the spectrum of neurons that are presynaptic to a given neuron look very different than the spectra of neurons overall there. So in any case, I very, very briefly want to mention quasi-experiments because that's what the Nobel Prize was about. Here, the question is, are there cases where we can know about causality in complex and potentially confounded areas? So here's an idea of from the econ literature. Let's say there's an exam that you take. There's an award that you can get in America, which is the Certificate of Merit. And if you're above a given threshold, then you get it. And if you're below the threshold, you don't get it. And the idea is this could be a way for us to test if there's a causal effect of getting the certificate on your life later. And the idea that makes causal inference in this case possible in domains where it's often not possible is we can reasonably assume that getting the certificate, your future achievement, however it's defined, will be a smooth function. In fact, if we can assume that there's noise in the exam score, then we can guarantee that. And then you can say, we only look at data that's close to the threshold, and we compare the ones that are below versus those that are above the threshold. And in this case, that difference is a valid estimate. And here we have data from the first experiments. Doing that, what you do is you fit on the left side, you fit on the right-hand side, and on the y-axis, what they had is the probability or the percentage of students that win a scholarship. Upper graph, everyone, lower graph, only those that win a major scholarship, and we find this big discontinuity. Here is Angrist's classical class size paper. There's the Jewish sage Maimonides said that no class should have more than 40 pupils. Israel follows that rule, and with that we can then look at that discontinuity, where we basically compare people who just barely made it into classes that are just smaller than 40 and schools that are just above 40, and he sees a big difference in their future performance outcomes. And then there's coming with these so-called quasi-experimental techniques are then sanity checks. If people would cheat, maybe rich people have their teachers like go over it and change their scores, you would see it in the distribution of, say, covariates like socioeconomic status in the overall data. I should also say we can look at the variance of the relevant estimators. It requires much more data, but it is causally much more valid. And I should also briefly mention this paper with Ben Lansdale, where we argue that this is a way for neurons to learn, and we can show that neurons can approximate gradient descent with it, and that it works under certain circumstances, namely high correlation works better than other techniques. And this brings me to the take-home message. I think causality is a central goal to neuroscience. It's hard to obtain in practice. If we're intracellular, we can use spikes as perturbations, and I didn't get to talk about it, but it's the same regression discontinuity idea. Even then, power is a major problem. Like you always, causal inference techniques basically cost you extra power for being causally more valid, and maybe causality is not what we should want, but that is for something else. And I just want to thank the rest of my lab that did all the work, and thanks everyone for listening to me.